Hello everyone, this is Jay Kim from Park Systems. Welcome you to webinar series on nanoscale research using AFM and techniques. Today, in this session, I'm going to talk about the AFM advanced mode, especially for nanomechanical properties measurement by AFM. Here's the contents of today's talk. First of all, briefly, I will introduce what is AFM. Next, I will talk about AFM nanomechanical mode, including force spectroscopy and pinpoint nanomechanical mode. After that, some important points for AFM measurement will be presented, and finally, comparison between AFM nanomechanical properties measurement techniques will be discussed. Okay, let's start with what is AFM. AFM is the technique for gathering topographical information of sample. It contains XY and G scanner, and probe including cantilever and sharp tip is positioned at the end of the G scanner. And using this sharp tip, our sample surface will be scanned line by line. In principle, the interaction between two atoms in here atoms of tip end and sample surface are utilized for imaging. Depends on the distance, two atoms experience the attractive or repulsive force, and using this interaction between two atoms, contact and non-contact or tapping mode imaging can be performed. Like these examples, many types of samples can be studied using AFM, from micrometer to nanometer size. Of course, one of the most powerful advantages of AFM is that AFM can measure almost sample type, such as soft, hard, complicated structure. Of course, also conductor and insulator can be imaged in air or liquid or vacuum condition. As I mentioned, AFM is quite a famous technique for height measurement, but we can investigate nanomechanical properties of material using AFM, the force spectroscopy mode. The force spectroscopy is the contact-based technique for studying nanomechanical properties such as Young's modulus, stiffness, and adhesion force across various types of samples. The force distance curve, here we can call the FD curve, the result of force spectroscopy, is a graph of force experienced by tip depending on the distance between the tip and sample surface. There are several interactions between tip and sample while measuring the force spectroscopy. This slide shows the process of single force distance curve, FD curve, measurement. At the first stage, the sample is approaching to sample surface, close surface, but there is no interaction because the tip and the sample surface have not yet been in contact with each other. Next, the probe jump into the sample surface due to the water layer of the sample surface. And at that time, the negative force signal can be detected. Also in this stage, the probe approaches to the sample surface. Next, the probe is pressed against the sample surface to a certain force. In this case, we can call set point, where the cantilever is bent. We can monitor it from photodetector like this, And after reaching to the set point, the probe is retracted. But before detaching between AFM tip and sample surface, because of interaction or adhesion between the tip and sample, the cantilever is bent. But at this time, it bends in opposite shape when pressed, like this. And finally, the tip and sample are completely detached. The probe returns to its original position. And this is the one cycle of force spectroscopy measurement. And the result, the FT curve is shown like this in this slide. Then let's look into the FT curve carefully. From the FT curve, we can obtain a few mechanical properties of sample. From the slope of approach or retract curve, the stiffness or Young's modulus can be gathered. And adhesion information also can be obtained from this retract curve. This minimum negative force in retract curve indicates adhesion force, and this area between the retract curve and the baseline shows adhesion energy between tip and sample. Here comes a few examples of FT curves in samples with different properties. In case of hard material, hard sample such as plastic, metal, glass, ceramic, they have very steep slope of approach or retract curve. And opposite case, the soft sample, like soft polymer or rubber, they have broad slope of approach and retract curve. And it means when we push the sample with a certain force, very small or almost no deformation can be detected in hard sample, and huge deformation in soft sample. Another case, when sample has low adhesive surface or less adhesion between tip and sample, just small negative force or area can be checked. In contrast, high adhesion sample or sticky surface or big interaction between tip and sample, like this, large negative force or area between retract curve and baseline can be shown. On this wise, depends on sample's property, we can monitor various FT curve pi. Let me show you one example of FT curve applications. The sample is cross-section of Kevlar fiber bundles and epoxy sandwich between those fibers. And based on AFM non-contact mode, the height image, the left one, and force spectroscopy mapping, the right one, were performed. And from this force volume image, the stiffness, we can see this stiffness contrast between Kevlar fiber and epoxy. And as I mentioned previous slide, this Kevlar fiber is harder than epoxy, and we can see this difference between these two materials from image and also FT curves. The slope of FT curve in Kevlar fiber is steeper than epoxy one. To make an accurate measurement and analysis, the cantilever has to be calibrated, and those three items are the main factors for them. The first one is a force slope correction, and it calibrates the force slope, which is changed in A minus B value according to the G scanner position. The second one is A-B sensitivity calibration, which is for converting the A-B displacement in volt unit into meter unit. And the last one is a force spring constant value calibration. And it is for the quantitative mechanical property measurement. And Sommertune or Zader method can be utilized for this spring constant calibration. From the FT curve, after force slope correction calibration, this flat baseline can be acquired. And using A-B sensitivity calibration, the deflection, volt unit, and low data can be converted force unit accurately. So we can get samples on Young's modulus after this calibration. In terms of Young's modulus, it can be calculated by using contact mechanics models in FT curve. The Hertzsprung model is generally for null adhesion value in FT curve, and DMT is good for hard material with adhesion value. And JKL is suitable for soft material with adhesion value, and Snedden model is for conical shaped AFM tip with somewhat big deformation. Okay, let's move on. Pinpoint nanomechanical mode. Simply speaking, the pinpoint nanomechanical mode, from now on, let's call it just pinpoint mode. This pinpoint mode is imaging technique for samples mechanical property, and it is contact-based technique, but AFM probe does not scan with the constant contact on the sample surface, but repeat this FT curve, this FT spectroscopy on each pixel with a fast speed. And using pinpoint mode, the imaging not only samples height, but also we can get mechanical properties of sample surface, such as modulus, deformation, adhesion, energy dissipation, and stiffness. And like this video, once again, after finishing one cycle of FT spectroscopy, the XY scanner moves a pixel to the next one, and this one cycle of FT spectroscopy, like FT curve, only takes a few milliseconds. The principle looks same as force mapping, but much faster than it. The continuous XY scanner and G scanner movement can be shown, and each FT curve is monitored and saved. So we can see mechanical properties information at every single point, and the image contrast, line profile, and numbers of each mechanical properties can be obtained. Total 8 channels can be recorded in pinpoint mode: the modulus, deformation, adhesion force and energy dissipation, stiffness approach, and retract. And normally, this Young's modulus and adhesion information are mainly observed, but researcher can be pick them up, depends on the research purpose. And I prepared some mechanical properties images using pinpoint mode. Like this result, topographical information and mechanical properties are gathered simultaneously, and we can clearly check the difference when two or more than two materials are mixed. Another example is in here. The sample is a black copolymer embedded in rubber, and we can distinguish two materials very clearly. And normally this pinpoint mode is quite suitable for this kind of polymer science. And one more thing, thermoplastic polyurethane, it was analyzed by pinpoint mode. And this adhesion force image shows a clear contrast between the materials. And here's look at some important points in Lear AFM measurement. The first one is the probe selection. As I mentioned before, it is very important to select a proper probe for AFM measurement. In general, when referring to probe information, the most frequently checked are the cantilevers, resonance frequency, and force or spring constant. And this slide is the cantilever information of NCHL probe, which is the most used non-contact probe. Here, it can be seen the NCHL has a resonance frequency of 330 kilohertz and spring constant of 42 Newton per meter. Among these various types of probe, we have selected a suitable probe for the imaging mode. For the contact mode of probe with a low spring constant value, here spring constant value of about 1 Newton per meter or less than 1 Newton per meter is recommended. For non-contact or tapping mode, a harder and higher resonance frequency probe is used. If a hard cantilever with a high spring constant is used in contact mode, damage to the sample surface can easily occur. And of course, this is just a common situation, and you need to check and you need to select on proper probe according to the sample and measurement conditions. For the details, proper cantilever selection is important to accurate mechanical properties measurement. In this case, we have to consider both the spring constant of the cantilever and stiffness of sample. When the spring constant of cantilever is much higher than sample's stiffness, only sample deformation occurs and no cantilever bending. And the opposite condition, if sample's stiffness is much higher than spring constant of the cantilever, no sample deformation and only cantilever bending occurs. And both cases, the Young's modulus will be improperly calculated. So similar level of spring constant of cantilever and stiffness of sample is always good for more accurate measurement. The next slide shows the discussion about sample type. Of course, AFM has the advantage of being independent of sample type, but these slide cases are conditions that make AFM measurement difficult. The first one is samples that are too heavy to put too much strain on XY scanner, or too large, like too big to load on XY scanner. And also, if the sample is not properly fixed to the substrate, like moving around, or a sticky sample, or dirty surface. These all conditions that make FM measurement quite difficult. And one more case, if the sample surface is dirty, it will be difficult to achieve the desired AFM result. As in this example, if this sample surface is contaminated with some fingerprint or organic matters, the desired sample information is distorted due to these contaminants. The scratch line information that researcher want to check is covered with this kind of organic material and cannot be identified. And in this case, of course, be sure to clean this sample surface, make a clean surface, so that only actual scratches can be checked like this. Next, I'm going to talk about some different AFM modes for measuring the nanomechanical properties. The first one is the tapping mode. The tapping mode is a basic AFM mode for height measurement, and the cantilever is oscillated nearby the sample surface and scanned. In non-contact mode, there is no physical contact between tip and sample, but in contact mode, the tip taps the sample surface. And while the AFM tip makes intermittent contact with the sample surface, there is phase delay between driving and detecting signal due to these mechanical properties of the sample. So we can get the relative physical properties of sample surface sample through this phase image. In force modulation microscope, the FMM, the AFM tip measures the sample height image based on contact mode. And at the same time, the tip oscillates against the sample surface to obtain the mechanical properties. The cantilever oscillation, amplitude, and phase change depending on the mechanical property of the sample as follows. And the nano indentation mode is just the same as FD curve measurement, but it is mainly for hard sample and permanent deformation occurred by very stiff tip and cantilever. Here is some comparison between the nanomechanical properties measurement. In FD curve, it is a spectroscopy type, but pinpoint mode is combined between the spectroscopy and imaging mode. Tapping, FMM is the imaging mode, and indentation is the spectroscopy mode. And the important thing is this quantitative analysis. Actually, this FD and pinpoint mode, and also this indentation mode, the quantitative analysis is possible, but tapping mode and FFM is not possible. So we can select some proper nanomechanical mode for the research purpose. Next is the live demo for AFM nanomechanical property measurement by our FX40 system.
Let me start live demo for AFM nanomechanical mode using by PARC FX40. The PARC FX40 is the new AFM model of PARC systems, and it shows high performance and fully automatic AFM system. Here, this screen shows Smart Scan Interface, which is PARC Systems AFM operation software. Using this software, we can control all things including AFM probe, sample, and all other measurement conditions. Today, I'm going to measure 3 polymer samples. The first, PDMS, the soft material. And the second one is a LDPE. It is harder than PDMS. Normally, the modulus of PDMS is about 1 or 2 megapascal. And modulus of LDPE is 100 to 200 megapascal. The last one is a blended polymer, and it can show clear mechanical properties contrast. For the AFM image, we should prepare a probe. Previous AFM, we have to load the AFM probe manually, but in this FX40 system, automatic probe exchange system do all things. Here, when you click this probe button, then FX40 system, go to probe cassette, and then click the load button. Then you can see the probe set. Oh, and you also can see this internal movement from this camera. So like this, we can see this probe set, and after that, click detect button. Then camera is focusing on this probe and recognized by QR code. For the measurement, I will use Cont SCL probe. It is soft cantilever, so it's quite good for polymer sample. Click this Cont SCL probe and click this pick a bed. Then FX40 system automatically load the selected probe. So yeah, the G scanner close to the probe. Load the probe and finding the position of cantilever and laser. Also, the alignment of laser beam and alignment of photodetector are performed without manual operation. So close this window, then you can see already this laser beam and photodetector are aligned. Next, click the sample, this sample button, click the load button, then you can see your samples on multi-snap-in sample chart. I've prepared 4 samples from the bottom left. This one, it is a sapphire sample for cantilever calibration. And top left one is the PDMS. And top right one is LDPE. And the last one, this bottom right sample, is the blended polymer. Using this mouse cursor, like this, you can select the measurement position and click Go To. So like this, all we need to measure is just a few clicks. It is ready for the measurement. For the macular nanomechanical property measurement, we should do the cantilever calibration. And the first one is force slope correction. To do that, just very close to the sample surface. In this case, I'm gonna change the camera setting to see the cantilever and sample surface. Okay. And click the approach button. The system automatically goes to sample surface for approaching. Okay, almost there. Yes, this cantilever approached on the sample surface. But for the force slope correction, we have to lift this probe up a little bit. In this case, lift up around 200 micrometer. And then go to the spectroscopy and select this FT curve, FT function, and set up the imaging parameters. And click the Start button. Then you can see FT curve, but it is in air. The FT curve was performed in the air without approaching or contact between tip and sample. And after that, click this calibration and select this force strobe collection. Then you can see one pop-up window. In this window, select the full range of this fitting curve and just click the apply button. And close this window and go to the scan and approach again. The next one is A-B sensitivity calibration. To do that, we need one FT curve, but after approaching. And this FT curve have to perform on very hard sample. Today, sapphire. First, after approaching, again, go to the spectroscopy and set up the parameters. In this case, I'll also set up this set point to some low value and click start button. Then system perform the FT curve on sapphire sample, and also we can get one FT curve like this. Same as force slope correction, click this calibration and go to cantilever sensitivity. Then you also can see this pop-up window, and from this pop-up window, select this fitting range and click the apply button and close this one. And after that, go to the scan and lift up a little bit, 2 micrometer. And the last one is the spring constant calibration. And to do that, of course, we have to lift the G scanner up a little bit and go to the spectroscopy again and click this calibration and go to cantilever spring constant. Then also you can see one pop-up window, but in this spring constant calibration, you don't need to measure FT curve. Just click this acquire button. Then system will detect this power spectrum density of this cantilever. And it requires approximately 1 minute, around 1 minute. And you can see this process from here. Okay, done. After finishing this sweep of this cantilever, you have to select this fitting range and click this calculate button. Then you can see this cantilever's on spring constant. And don't forget this save button and close this window. Okay. This process is for cantilever calibration, and of course, if you want to do some accurate measurement or accurate calculation for Young's modulus, you have to do these 3 processes. Okay, let's start measurement on PDMS sample. To the movement, lift up a little bit and click the sample button and move this cursor to PDMS and click the go to button. And then close this window. Oops, sorry. And go to the scan and click approach button. Now before that, I'm gonna change the set point to some higher value. This G scanner close to the sample surface for the approaching. It's almost there. Okay, approached. And after approaching, click this advanced button and select this pinpoint. Here in this pop-up window, we can control the parameters for pinpoint mode. Just briefly, this speed means a G-scanner speed, and set point means maximum loading force. And this real-time FD, if you activate it, every single FD curve of measurement will be saved. From this detail tab, when you click this dot, you can see some parameters. Also, we can control this baseline of minimum length, threshold for Young's modulus calculation, and also we can control this G control related, and also this modulus related. From this modulus related, we can select the contact mechanics model like halogen, DMT, JKL. Also, you can select or you can change this tip radius. In this case, I'm gonna change this speed and set point. Here, minimum length will be 15 nanometer, enough. Oh, and then activate this pinpoint scan. Then you can see real-time FD in here. Okay, and go to the scan area and set up the scan size. Then you can see this modulus value with height image. Also, other mechanical property information you can check, like this. When you click this adhesion force, you can select other channels. Let's start scan. Then from this window, you can see real-time image, and also corresponding this line profile can be checked from this scan trace. And when you click this G height, also you can change the channel you want. Modulus one is in here. And one more, if you click this scan data, then you can compare the channel information like this from G height and how about the modulus. One click, then you can see G height and modulus value. And when you click this line profile from previous one to modulus, then you can also compare this line profile as well. Let's back to the scan position. And I think we can skip this imaging process. But anyway, like this, we can see this G height image and also line profiles. Also, we can check real time this modulus value or this other mechanical property value from this cursor. Click the cancel button. And let's move on to the LDP sample. Okay, deactivate it and lift up a little bit and click this sample and move to LDP and click Go To. And after that, close this window and approach. Almost there. Okay, it approached. Then other thing is just same as PDMS. Click the advanced and go to the pinpoint and activate pinpoint scan. And here, let's change the parameter a bit. Okay. Oh, yes. JKL will be better. Then you can see this real-time FD curve. And let's set up the scan size, also 5 micrometer. Actually, this PDMS and this LDP is just one material, so they don't show some contrast, but we can check this well-matched modulus value. The previous one is around 5 megapascal on PDMS, and this one, the LDP case, is about 100 to 200 megapascal. So let's click the scan button. Then we can see this kind of modulus value, as well as this other mechanical property channel value. Also from this scan data, we can compare other channel information. Like this, we can check this morphology of scan sample surface with this mechanical property information. To save our time, let's skip this sample and let's go to the last one. Click the cancel and set up to 0 and deactivate scan pinpoint scan and lift it up a little bit and click the sample and move cursor to this blinded polymer and click go to. And then close this window and approach. So after approaching, let's clean this window. And oh yeah, this is blinded polymer. And other imaging process is just same as the previous one. Go to the advanced and click the pinpoint and activate this pinpoint scan. And when you set up this scan size, in this time, 50 micrometer, then you can see this real-time FD curve, and after reaching the one line, you can also see this line profile. And also you can change your imaging area by using this mouse, like this. In this case, let's go to a little upper area. Then the scanner go a little bit up. And also, we have one more option for saving the time. When you click this option, you can see this skip scan. If you activate this skip scan, the system scans forward or backward only. The previous time, we performed scan both forward and backward, but if you activate this skip scan, the system just scan forward or backward only. In this time, scan forward only. Let's click the OK button and let's start scan. So like this, we can see this G height information as well as other mechanical property information. Let's compare between G height and stiffness approach. Here, stiffness approach. So like this, we can see some different mechanical property between this region and this region. Should be this bright area has some more high modulus or more harder than this dark area. So like this, we can compare these two blended material with this G height information. So go to the scan position. Okay, modulus is also same as this stiffness one. So G height, we can see some interesting structure in here. Okay, like this. In the case of this blended polymer, we can recognize some blended these two materials. We can recognize these two materials. Okay, let's cancel. Let's skip this sample. And after finishing all the measurement, set up the zero size and deactivate the pinpoint mode and lift up a little bit and click this probe and select this blank slot and click this part into. Then like this camera, this system automatically unload this probe to probe cassette. So in conclusion, we can successfully study the various polymer samples using pinpoint nanomechanical mode. And in this mode, mechanical properties such as modulus, adhesion, deformation, and others can be investigated with height information.
Okay, here is the summary of today's presentation. Using force spectroscopy and pinpoint nanomechanical mode, we can obtain mechanical properties information such as modulus, adhesion, and other properties with height information. AFM probe selection and sample preparation are very important for accurate measurement. And there are few AFM nanomechanical modes, so we can choose proper modes for measurement purpose. This is the end of today's webinar. Thank you very much for your attention, and please feel free to ask me if you have any questions or comments. Thank you very much.
Okay, so that is the new product launch by Park System, FX40. So right now we have a few questions coming in. So that I will ask to Dr. Jake. So Dr. Jake, the first question is the measurement of Young modulus using this software after FD accurate? Or is it better to calculate the Young modulus by proper curve fitting software such as Origin or MATLAB?
Hello, can you hear me?
Yes, I can hear you, Dr. Jake.
Oh, yeah. Actually, yeah, we can measure the Young's modulus by our own software. Of course, the Young's modulus was calculated by some two-point method, and the fitting was by the two-point method. And also, we can get the FT curve, the on-FT curve, so the researcher or user can analyze the FT curve by Origin or other software as well.
I see. Yeah, I hope this answer to the questions of the attendees. So the next question is, what is the maximum stiffness and hardness that our AFM can measure?
So our maximum, the modulus, the measurement, modulus or hardness measurement level, you mean?
Yes.
Well, using the FD or Pinpoint, we can measure 10 or more than 100 gigapascal. But I recommend if your sample has like 10 gigapascal or more than 10 gigapascal, I think the nano indentation is the better, because we can get the number, we can get the modulus more than 10 gigapascal, but sometimes the result is not accurate. So I can say, so we can get some high value like a 10 or more than 10 gigapascal, but if your sample has more than 10 gigapascal modulus, the non-indentation will be better.
All right. So I think we are quite close to the end of the webinar session. So let me take one last question. So the rest of the questions that are typed in, we will answer by email due to time constraint. Okay, so Dr. Jake, the last question is imaging and calculation of mechanical properties can be done simultaneously or separately?
Of course, simultaneously. So as the live demo session, so you can see the height image with other mechanical properties image simultaneously. And also you can see the difference with the line profile, of course.
All right. So that is the end of today's webinar. So thank you very much, Dr. Jake, and thank you very much to all the attendees that is on the line today. I hope the webinar is information and helpful to your research. If you have any question, please feel free to contact us. Thank you very much and have a good day. Bye-bye.